This block and bleed manifold works because it combines multiple critical functions into one compact unit. The clever bit here is its ability to ensure absolute isolation. It's designed to isolate fluid flow and then safely vent any remaining pressure downstream. This is crucial for maintenance and repair. Imagine needing to work on a pressure transmitter. You must first stop the fluid flow completely to ensure safety. The block valve, often a robust ball valve, is the first line of defense. It physically stops the fluid from moving past it. Once the block valve is closed, the downstream side is isolated. But is it truly safe to proceed? Not yet. The minor setback here is that even after blocking the main flow, there could still be trapped fluid or residual pressure. A single valve isn't enough. This trapped energy poses a significant safety risk to anyone working on the downstream components. It's an invisible danger. Even a small amount of pressurized fluid can cause injury or damage if a component is disconnected without proper depressurization. This is where the bleed valve comes in. After the block valve is closed, the bleed valve is open to vent any remaining fluid. This venting process ensures that the downstream side of the manifold is completely depressurized and free of fluid. It provides a visual and physical confirmation that the system is safe to work on. This verification step is critical for safety protocols. Without this bleed function, relying solely on a block valve would leave an unacceptable margin for error in many industrial applications. The bigger problem is not just isolating and venting, but doing so reliably and efficiently in complex high-stakes environments. Historically, achieving this level of isolation required multiple discrete components: a block valve, a separate bleed valve, and all the connecting pipework. Each connection point in such a setup is a potential leak path, increasing the risk of failure and requiring more space for installation. The challenge was to simplify this complex arrangement while maintaining or even enhancing safety and functionality. The solution was to integrate these functions into a single purpose-built component, the block and bleed manifold. This integration significantly reduces the number of potential leak points. Fewer connections mean greater integrity. The body of the manifold is typically machined from a single piece of metal, ensuring robust construction and minimal internal pathways. This compact design also saves valuable space in crowded industrial installations, making maintenance access easier. The operational sequence is straightforward. First, the upstream block valve is closed to stop the main flow. Next, the bleed valve, typically a smaller needle valve, is opened. This releases any trapped pressure or fluid from the downstream side. This sequence ensures that the component being serviced is completely isolated and depressurized before any work begins.
The choice of valve types is also deliberate. Ball valves are excellent for quick, positive shutoff, while needle valves offer precise control for venting. Some block and bleed manifolds incorporate two block valves, creating a double block and bleed configuration for even greater isolation security. This redundancy provides an extra layer of protection, especially in applications involving hazardous or high-pressure fluids. The manifold design also simplifies installation. Instead of installing separate components, you install one unit. This reduces labor time and the potential for errors during assembly, contributing to overall system reliability. The block and bleed manifold is often used to interface with pressure measurement devices like gauges, transmitters, and switches. This allows these instruments to be safely removed, calibrated, or replaced without shutting down the entire process. The counterintuitive engineering mechanism is the reliance on two distinct actions, blocking and bleeding, to achieve one goal: absolute, verifiable isolation. It's not about doing less, but doing more in a smarter, integrated way to achieve a higher standard of safety and operational efficiency. The manifold itself acts as a compact, self-contained safety system, reducing the footprint and complexity of traditional valve arrangements. This design principle is applied across various industries, from oil and gas to chemical processing, wherever fluid control is paramount. The block and bleed manifold is a testament to how thoughtful engineering can transform a series of individual problems into a single, elegant solution. It's a prime example of how combining existing technologies in a novel way can yield significant improvements in safety and operational efficiency. The design ensures that maintenance personnel can confidently work on downstream equipment, knowing that upstream flow is truly blocked and residual pressure is vented. This meticulous approach to safety is what defines good engineering, where every potential failure point is considered and mitigated. The block and bleed manifold is more than just a collection of valves. It's a carefully engineered system for critical fluid control. Its design ensures that the fluid from upstream of the manifold does not reach other components of the system that are downstream.
And then, crucially, it bleeds off or vents the remaining fluid from the system on the downstream side of the manifold. This dual action, integrated into one component, is the core of its ingenious design, providing both isolation and verification. The block and bleed manifold, by combining isolation and venting into a single robust component, provides a secure and verifiable method for safely working on fluid systems. It resolves the inherent danger of residual pressure and the complexity of discrete valve setups, ensuring that maintenance can be performed efficiently and without compromise to safety. This ingenious component stands as a cornerstone of industrial safety, a testament to how clever engineering makes the complex safe and the dangerous manageable.